Okay, so then where we're at, excuse me, is we're going to kind of complete panel data today. We're doing a lot of work in Stata, so we don't really have a lot of slides and kind of theoretical conceptual work to work through. So we'll be doing a lot of work in Stata here. Just as kind of a reminder, so that kind of problem set, I had it switched to be done today yesterday. So I'll try to start getting those graded here tomorrow. I'll post up a solutions file tomorrow as well. And then that quiz is kind of due by the end of the day today, that fifth quiz. So outside of that, we've got one quiz and one problem set left. So tomorrow you'll see that sixth problem set posted. I think relative to what we've done in the past, this problem set might actually be a little bit easier. There's not as many kind of follow-up questions. A lot of it's going to be more just kind of doing this work in Stata, kind of showing me your code. So there'll be, I couldn't say it's necessarily easier because the topics are more advanced, but it might take a little bit less time than some of the other problem sets. I also put up the next set of kind of practice problems. So next week, I'll have that problem set up. We haven't covered all the material next week. So that problem set, you won't be able to work through the whole thing until after next Thursday's class. So I'm going to have that set to be due at the end of the day, Thursday, that week before finals. Now, with finals and things, I would suggest working on it early. That way, once we do start covering material next week, you might even be able to get through most of it after Tuesday's class. So kind of working on that, getting it done early. But should have, more than enough time to kind of work on that. We'll have a whole week after we cover the material next Thursday for you to submit that in the following Thursday. For the quiz, I would start kind of practicing that early as well. I'm going to have that due date set to be the end of the day, Thursday as well, that week before finals, but you can take it quite a bit earlier. Once again, we'll cover all the material after next Thursday. So kind of a week to complete each after we go through all of the material next Thursday. So that week before finals, we won't have class that Tuesday. So I'm gonna have to cancel class. I will post a replacement video of me working through a handful of questions from this practice exam. I will also tomorrow get up a second practice exam, and I probably won't go through every question in that posted video, but that Thursday before finals we'll still meet. We'll have no new material, but basically we'll just be doing exam review. Okay. So next week is the last week of new material. We'll have class that following Tuesday, and then kind of review session or review class that Thursday before finals. Okay. And I'll mention more kind of about the structure and thing of the final as we get closer. So probably towards the end of next week, and then that week we're doing review. We'll talk a little more specifically about number of questions, kind of what topics you should be kind of reviewing. But it's not going to be cumulative in the sense that I'm only going to ask you questions since we've covered in the last exam, but it's comprehensive in the sense that like everything we're doing, right? We're still looking at statistical significance. We're thinking about standard errors, making predictions. So in that sense, it's comprehensive, but I'm not going to go back and ask you like simple linear regression questions. Okay. So that's kind of a roadmap of where we're going. Any other questions for me before we kind of dive into things here today? Okay. So where did we leave? Oh, I had this pulled open. I forgot. This is what I want. Nope. Yep. There you go. I thought I had it open. I must not have clicked on it. Double clicked on it. So we left off thinking about fixed effects. Okay. So we said, what are fixed effects? It's essentially just a slightly more complicated way of, when we went all the way back, if we had a categorical variable, we could include a dummy variable for every single possible response. The difference is here, it's almost like what we want to include is a variable for each individual's ID number. Essentially, if we had a panel data set, different individuals across different time periods. But in some data sets, we've got hundreds of thousands. This is going to take forever for us to do manually. And so we said we can kind of take that variable. If it is numerical, we're fine. If it's not, we can kind of use that encode command to force it to be kind of numerical. So even if I had names, I could assign every name a different value. We could then include essentially a dummy variable for every single person's ID. Now, obviously, like writing this out by hand is like, would take us forever, but we can kind of do this and state it pretty quickly. And that's kind of our idea of fixed effects. Now we said we could do a similar thing using kind of first differences, and it would give us kind of similar results. The problem with first differences, if I take a difference, what happens the very first year in my data set? Can I look at the difference between 2020 and 2019 if my data set starts at 2020? No, so I lose a little bit, I lose some observations. What's the problem with losing observation? What is that going to do? Increase my what? So the more observations I have, what's going to happen to my statistical significance? It's going to go up because my standard errors go down with more observations. So that first difference approach, although I'll get similar estimates for my coefficient, I'm going to lose some statistical significance because I'm essentially losing a year of data. Okay. Now that doesn't matter if I've got 50 years of data, a whole lot, but if I've only got 5 or 6 years of data, that's going to be a sizable proportion of the overall observations I have. So ideally, we kind of prefer this fixed effects regression for that very reason. Okay. Now, what is one thing that's going to be impacted in our fixed effects regression that wouldn't be impacted by our first difference regression, assuming we have no loss of observations? So I'm including in a bunch of dummy variables. What's going to happen with certain statistic? My R squared will go up, right? So including all these additional variables is going to automatically increase my R squared, right? So what statistic would we want to focus on to see if this fixed effects regression is actually better at making predictions about those Y values? I compare it to I would use my adjusted R squared, right? So it would have to be, if I think about it this way, if I'm comparing kind of my typical regression, I'll just write one, I'll write one control variable in here just to kind of make it easy. You know, if I look at my adjusted R squared here, let's say it's, I don't know, 0.5. Once I use my fixed effects model, it's essentially like I've included all of these different controls for every single individual, or a bunch of different dummy variables. So if we think about kind of our adjusted R squared, we were going to have, it was essentially like our R squared times what, the scaling factor, something like this. Right? So we said whatever kind of the amount of the variation in Y we can explain, well, including these fixed effects is going to increase that. And I think a little bit incorrect here. It's 1 minus kind of what we can't explain. But here we can think about this as that's going to increase my R squared. But what happened is I include more variables, right? And actually here I should write this as, this was essentially 1 minus the R squared, sorry, because it was the proportion we couldn't explain. Well, the proportion we can't explain is going to go down, right? Is that what I want here? No, this is going to be, the scaling factor should be n minus 1 over n minus k minus 1. So if we increase k, going to decrease this, increase this, and then, sorry, no, here's my actual equation, right? So as I increase my R squared, the amount that I can explain, the amount that I can't explain is going to go down, but increasing the scaling factor decreases this, sending this part up. So they're working in opposite directions. Right? As I add more variables, I can always explain more. So the amount I can't explain would go down. But by including those additional variables, the scaling factor is going to over penalize me. So I don't really know what's going to happen to my adjusted R squared. Could go up, could go down. Depends on how much these fixed effects kind of reduce the proportion that I can't explain in that Y variable. So ultimately, the end result here is going to be what's happening to the adjusted R squared? We don't know. Depends. Right? So here, if we kind of take a look at this, right, we did this in Stata last class. So I've got my global path. I think we had this first player shot data that we were looking at. It was a little bit large, so it's taking a second to load. I think here we shouldn't need anything. Oh, wait, sorry. We look at the birth data set. And we come down here, what we were doing last class. So we had to encode that state variable. And we said there really are three ways of kind of running these fixed effects. Right? So we have this variable, in my case, not individuals, but each state. So I could use the IDOT command. That's kind of similar to what we do with the categorical variable. It would then include a dummy variable for every single state ID. We could also use this areg command. It's just another way of kind of absorbing that variable when we include fixed effects for, where it essentially includes all those dummy variables for us, which we said, that's kind of nice because, here I've got 50 states. If I was doing this like with that player shot data, I'd have every single player here. That's going to be a lot of output for state to give me. That areg command is nice because it just gives me the coefficients of the variables, not all of those coefficients on every single dummy variable for every single state. But still gives me the same value, negative 33.4. All right. So there's two different ways of doing the same thing. And then we had kind of this third way, which was kind of use this xtreg command and then tell it I want to use fixed effects. So the reason why ultimately I'll start using this is because outside the next level of this class, with panel data, there's things like random effects you could start using. And there we need to kind of use that xt kind of built-in regression command for stata. Now, when we run that, right, it still gives us that exact same coefficient. Right? So it's just three different ways of doing the same thing. Ultimately, once you kind of get outside of this class, that IDOT command and the areg command have some limitations that the xtreg command doesn't. So you can do not just fixed effects, you can do random effects and some of these other things. So usually we kind of, if you're looking at someone else's code, you'd probably see them use this command. Okay? Maybe not for just simple fixed effects, but if we were kind of continue on to kind of more advanced topics. So that's where we left off thinking about fixed effects. There's actually another way we can do this, right? So this way, it's going to take us more time, but it's valuable in thinking about why it's going to give us the same result. Okay. So if I have panel data and I just run this kind of simple linear regression where I don't include those fixed effects, if I wanted to know the average kind of Y value for, in our example earlier, for every single state. So I look at every state and across these different time periods, I calculate their average. I think it was birth weight and GDP we were looking at. Or not GDP, what was it? Birth weight and, mother's age. Okay. Well, for every state, I could calculate their average for those two variables. If I did that, well, what's the average of the constant? Constant's always the same. It would be just the constant. Right? If I then take my Y values and I subtract the average Y for every single group, or essentially what we would call demeaning the data. So for example, Indiana, right? I would have Indiana's average birth weight in 2018. I would subtract from that Indiana's average birth weight across every single time period. So what that's going to do for me is kind of, I'm taking the mean out of that variable. Really, I could just take this equation and subtract this equation. And this is what I'd be left with. Notice the constant cancels. Right? I just rearrange this. My coefficient, I could now see this is going to be not on the x variable, but on the x variable d mean. Right? So it's the effect, essentially, of if in this state, their x variable goes up by 1 unit relative to their average, what would kind of the increase in that y value be relative to its average? And then my error, if I'm taking the error term, subtracting the average, well, here this is just kind of scaling my error because on average, my error term, the expected value should be 0. So we can demean our data. And what that's going to do is it's going to control for every factor within that state that was constant across time. That's what our fixed effects are doing. All right? It's saying whatever factors we can't observe that are in this state, so let's say I don't know what the state's average excuse me, I don't know, money spent on healthcare, right? Which would impact the birth rate of the child. Well, I don't have data on that. I'm creating omitted variable bias. Maybe I don't have data on what was that state's, I don't know, religious district, or like religious makeup. Well, that's going to influence kind of births, who's having births, and potentially the birth rate of the child. I don't have that data. All that omitted variable bias is going to exist. But when I'm looking at the average across every time period, if those things within that state are constant across time, I'm essentially now controlling for that, just like when I included a dummy variable. So if we take a look at this in Stata, how would we do this? Okay. So I want to run this regression where I'm predicting average birth weight in the state and the average mother's year, or sorry, the average age of the mother, right? I could use a fixed effects model, and we kind of see what that coefficient estimate is going to be. So we can start to use this by sort command. And what that's going to do is, okay, look, by this state fixed effects variable I created, which was just a number given to every state. So this would say, okay, take Indiana, calculate this EGen mean. That was how we calculated means way back in, I don't even know what week, right? Calculate this new variable. I'm going to call it birth weight mean. But what this will do, because I included the by sort command, is it calculates the mean of the birth weight variable just for that state. So like just for Indiana, it calculates the mean across every year for Indiana. And then what it does for all the observations where it's Illinois, it calculates just the mean for Illinois, and so on and so forth. So I'm going to do that for both my Y variable, which is birth weight, and this age variable, which is my kind of X right-hand side or independent variable. So when I do that, unlike when we were using that EGen command before to calculate a mean, that just made like one variable that was equal to the mean, right? Now, if I look here, oops, can I get this up? There, it's on the same screen. For Alabama, those values are always the same, right? Because it's the mean birth weight and mean age in Alabama across every time period. But then for Alaska, those values are a little bit different, right? Because it's calculating Alaska's mean birth weight across all those times. So what I can then do is for every year, I'll take the value that that state had, the number of births, or sorry, we weren't using that variable. I could take the birth weight of that state in that year, subtract the mean. Do the same thing for our X variable, which was the mother's years of age, subtract the mean from that. So the way that we would do that with our code is just say, okay, generate this new variable, in fact, two variables, right? So we've got a Y and an X variable. So take that average birth weight in that time period for that state and subtract the average birth weight across every time period. We would then go down to the same thing for mother's years of age, name them whatever we want. Just kind of making sure we know these are the D mean variables. So, one thing I put minus average here, maybe because I use this terminology a lot. Maybe you want to call it something like, this is my birth weight variable, but D mean, right? I'm subtracting the mean. Just whatever helps you remember what this variable represents, okay? So once I create those variables, and look at the data here, we'll notice some are going to be positive and some are going to be negative, because some years the birth weight in Indiana was above the average birth weight in that state. In other years, it's going to be below. So don't be afraid if you create this D mean variable and now all of a sudden, like, these values don't seem to make sense, because I just went from birth weight and like, I forget, this was like grams, so it was in the thousands, right? To now it's like negative, or how can you have a negative birth weight? Well, that's because when you demean it, it's how many units away from the average of that state was that kind of birth weight in that year. So we've got these demean variables. What we're then going to do is run a regression using those variables that we kind of subtracted the mean from. If what I'm telling you is true, we should get the same results. And that's because what a dummy variable does is it only controlled for everything that was constant across time within that state. Well, if I calculate the mean of one state, that captures all of the things that were constant across time in every single, it's doing the exact same thing. So if I now run this regression with my demeaned variables, Sure enough, I get the exact same coefficient. So we now have another way of doing this, right? We had first difference regressions, we have fixed effects regressions, and we now can run the same regression, or sorry, get the same results, but by demeaning the data. Okay. Now, we'll kind of notice here, we won't dive into exactly why. That would be kind of the next level of an econometrics class. But demeaning the data is, so if you think about every single year, when I demean the data, the error for that year could be different given the error that exists for that specific time period across all states. So what will happen if we use this demeaning approach? What happened to my standard errors? They were a little bit different, okay? So we won't dive into the reasons why or kind of the solutions to this. That would be like the next econometrics. So what, 471, I think, is the next course that you would take, unless you're graduating and getting out of here. But we're just going to focus on, it's a different approach and it gets me the exact same coefficient. And what's a nice way about this approach as well, compared to like first differences, is what happens to my sample size. I don't lose any data. So kind of the advantage of fixed effects, including dummy variables for every state, or demeaning the variables, is that I don't lose data like in that first differences approach. Okay. Any questions on anything I've said, or kind of any of the code or anything up to this point? Okay. Now, I had all this set up into thinking about maybe there was things that were consistent within a state, but across time, right? And I think in this example, that makes a lot of sense, right? There's things in Indiana that remain constant across time that are very different than Alaska. So when we wanted to control for things that were time invariant, did not change across time within that same state, we included state fixed effects. So maybe if I write this out, this will kind of help sense, right? So if I think that within a state, there are things that are constant across time, then you can almost think about what we really wanted. And when I was calculating like those means to demean the variables, is that we were thinking, I've got state one, and I've got time period or year, I don't know, 2010, 2011, 2012, 13. What I wanted to do here was kind of use state as my subject and then control for things that were constant, or what we would call time invariant, right? They're constant across time. They don't vary with time. So what did we do? We included fixed effects at the state level, right? So when I included dummy variables for every state, that controlled for things within that state that were constant across time. This is where it's going to get kind of weird in the context of this example. But what if I instead thought that there might be some things I want to control for? And this would probably make more sense if I was doing something like, oh, I don't know, wanting to predict exports and I don't know, here I was thinking about something like, I don't know how it calls, like world stability, the number of wars or the number of things going on in the world. Well, here, I might think that it's not that things within the state matter. These are things like at the global level. So every year that's going to look different. So, excuse me, what I might want to do is I might think every country is going to be impacted in the year 2020 by COVID, right? So that would be a good example. Or maybe in 2025/2026, they're being impacted by this war that it's going to have created, right? So there's things that are going to affect every country within the same year. Or constant across state in our other example within the same time period. So if that's the case, I think about I'm wanting to control for things not that are constant within that state, but that are constant within that year. So what would I want to include here? I would want to include fixed effects for whatever my time variable is. And this could be, look different in different examples. So I think about like another one. Maybe you can take like a financial economics course or finance and money. So if I'm looking at like the stock market and I was looking at something like different companies across time, what might I want to include fixed effects for? So yes, there would be things that are specific to that company, but let's say I had like, but a lot of times there won't be as many things that are consistent. Like let's say I'm looking at the same time period, but I have like weekly data. Well, each week I think there might be shocks that would impact every company equally, all right? But those shocks will be different every single week. So they're constant across my companies, but they vary. Sorry, they're constant across my companies, but within the same time period. So and that would be another example where I wouldn't use year fixed effects. There I'd have weekly fixed effects. So sometimes you want to include fixed effects for like your subjects, companies, countries, states. Sometimes you might want to include fixed effects for the time period in your panel data set. Years, weeks, days, months, whatever that time variable is. Okay? Now they'll be controlling for very different things, right? Subject fixed effects, so doesn't have to be state. That was the example that we used here. But whatever my subject is, states, countries, individuals, companies, that's going to control for things that are constant within those subjects across time. My time fixed effects, this could be years, months, weeks, etc. That's going to be things that are constant across my subjects, right? Excuse me, but within the same time period. So we're really controlling for two very different things, whether or not I use subject level fixed effects or time level fixed effects. Okay? Does that make sense what I'm saying?
It's like you can calculate the variances throughout states.
So the variance of what?
Like when you say when you talk about like a company or something like that, but like if there's like a shock, what is the variance like go up through?
So the variance, so you're thinking about the coefficients or?
Yeah, the coefficient.
Yeah, so depending on kind of what fixed effect I'm using, that would influence my standard errors differently, right? Of whatever my X variable I'm interested in. Yes. So what direction is a more complicated answer that we wouldn't dive into. We're not going to dive into this class. But yeah, if I use different fixed effects, I mean, first of all, I'm controlling for something different. So I'm eliminating a different omitted variable bias, in which case it's not only going to change the size of my coefficients, but potentially my statistical significance as well. So so when we say variance, we want to be careful. It's not the variance of the variables themselves, it's the variance or the standard error we're getting on our coefficient estimate. Is that what you were? Excuse me. Okay. Any other questions here before I keep? All right. So how would I do this in Stata? Honestly, we've already talked through it, right? So let's say now instead, I'm using the same example, but I want year fixed effects, the time period. Once again, three ways of doing this. I can use that IDOT command. I can use this areg command. Those will essentially give me the exact same thing, right? So 18.22, 18.22. The only difference is that if I use areg, it doesn't show me all these indicators. Well, here I only had 5 years, but you can imagine, let's say I had stock market data across every single day for the last 10 years. I don't want to see, right, a dummy variable for every single day, week, year combination. I just don't, right? I mean, first of all, it's going to take Stata a long time to do that, and then I have to scroll all the way up to look at the variable I actually want to know the causal effect of. So our areg command kind of avoids that. Now I could also use this xtreg, but here's where I have to do it a little bit different. So I think in the context of this example, it made a little bit more sense, and I think the way that the data downloaded, we kind of had our states and then every year for that state. That's how we would want to organize the data if we wanted state level fixed effects. If I want year level fixed effects, what I need to do is sort the data by year first and then by state. So for the year 2020, I would have every single state. And then for 2021, then I would have an observation for every single state. Once I set it up that way, now when I use that FE command in my xtreg regression, it will include fixed effects now for not my kind of state. I'm going to have to set this up differently where I've set it up year by state. It'll include fixed effects for my year. An easy way to remember this is when I use that xtset command, whatever I put first, that's what I'm wanting to include fixed effects for. So when it was we wanted to have state level fixed effects, we set this up by state and year. Whatever I want to include year fixed effects, I set my panel data up by year and state or time subject. Is that clear what I'm saying there? So depending on the fixed effects I want, I have to set this panel data set up differently. Maybe, where are we at in time? No, I think so maybe this will help make it a little bit more clear. So let's say I set this up so that I was sorting the data by state and year. So maybe I have Indiana, right? And then I sorted the data next by the year. I then have, I don't know, California. And I have it then sorted by year, et cetera, for every state. When I set the data up this way, so that was kind of using that xtset state year. So essentially what xtset does is it sorts the data by state and year. It would then say, okay, for this very first state, across time, include like an indicator variable for, or dummy variable for, was it Indiana? And then for the next state, include another indicator or a dummy variable for, sorry, was it California? So however I set it up, whatever I sort it by first, that's what it's going to include fixed effects for. If instead I use that xtset command and I do it by year and then state, what it's doing is it's saying, okay, for 2009, put in Indiana, California, et cetera, every single state. And then 2010, Indiana, California, et cetera, So what this is doing when I now include fixed effects in Stata is now it's going to include an indicator for 2009, 2010, et cetera, or essentially whatever I put first in my xtset, that's what I'm including fixed effects for. Any questions on this? This is just kind of maybe a good way of visualizing like what this xtset is doing with the data set. It's essentially just sorting it first based on this variable, and then second based on the next. And then whatever variable I sorted by first, that's what it's going to include fixed effects for when I use that FE command with xtreg. Okay. So now I'm going to kind of look at this regression where I want to include time fixed effects, not state fixed effects. So once again, these two gave me the exact same results. So it was what? 18.22. If I use this third way, I should still get 18.22. So I'm getting the same results because this is now including my fixed effects for each year. So 3 different ways of doing the same thing. Now I have a fourth way. A fourth way I could run this regression, which we said was to demean the data. Now this is a little bit different than what we did before because, and here I'm going to drop our old variables just because I'm going to use the same names. If you wanted to, you could kind of change these names just so you didn't have to drop them, but I'm going to drop them here. So what we're now going to do is because I have, excuse me, I now am looking at wanting to include year fixed effects. I want to control for things that are constant within that year across states. So what I actually want to do is create the mean not by state, but I want to find the mean by year. And then for that, now I'll look at my two variables and I'll subtract the mean within that year from the original X and Y variables. So here we had birth weight and mother's age. So now instead of by sort that state variable, I'm doing it by sort whatever my time period is of the year. So now I'm not calculating the average within that state across time. I'm calculating the average within that time period across states. And that's the mean that I'm then subtracting from these original X and Y values. So here, it looks very similar to what we were doing before, but I'm just doing this not by state. I'm now calculating these means by year. And then I'm taking the original values for X and Y, that mother's age and average birth weight, and I'm subtracting this mean that is not calculated within a state, but within a time period. So if I do this, right? Oops, sorry, I have to run this. I didn't run this yet, did I? So I'll kind of do that, run my regression with my new variables that are demeaned. Once again, if it helps, call it something like birth weight demean, something like that. Now when I run this regression, sure enough, I get the exact same coefficient estimate if I was running a fixed effects, just including dummy variables, right? It's doing the exact same thing there. Now, once again, my standard errors, although not very different, will be a little different with this approach. Whoa, any questions before we keep moving here? So something I want to point out with these results that I sometimes get questions on, but no one asked. It's kind of a weird thing. Oh, I want that. Hold on. There we go. I wanted that to go away. So when I showed you this demeaning equation, what do you notice that looks a little bit different about it than any other regression equation? What's missing? I've kind of got like my Y, my X, my error. Where's beta 0? Where's my constant? Well, when I demean the data, it's almost like I'm setting everything so that it has a starting point of 0. Because if I'm exactly equal to the mean, then my starting point is 0. So when we look at these regression results, when I was so if I looked at like the fixed effects model, there is some constant, right? And then for every dummy variable, it like changed where that starting point was for every time period. When I've demeaned the data, now what is the value of my constant? Essentially, it's 0. Now it looks like it's not 0, but why can I say it's 0 here? What's the p-value? P-value is 1, right? So what levels can I reject at? I mean, none. In fact, I couldn't even reject at the 0.1% level, right? So essentially, this is telling me my constant in these d-mean regressions, I'm setting it to be 0. And that's because my interpretation of this regression is going to be a little bit different. Right? It's still a 1 unit change in my X variable would cause the predicted change in my Y variable to be 18.2. But we actually have to say it a little bit different. It's if the X variable went up by 1 unit, starting from its mean, right? So it's still a 1 unit change. It's just that we've changed the starting point, right? The starting point is now that state's mean. So I wouldn't be as nuanced to ask you like the difference in that interpretation, but it is a little bit different, and that's why we get this new constant, which will be 0 in these d-mean regressions. Okay. So even though it's the same way of getting that same coefficient estimate, there are some differences across these approaches. Now, for the sake of what we're doing, we don't need to be as, dive too deep into it, but things like this, I would want to point. Like if I ask you a question, what's the constant from a regression where I demean the two variables? It should always be 0. So the other thing that I wanted to make sure we talk about, so actually before I do that, let me make sure I got through everything up to this point in our data set. We got what, 35 minutes? It's okay. If it spills over a little bit in the next week, it won't take us long. So I just wanted to make the point. In this example, it's likely there are things that are constant within a state across time and that are constant within the same year across states, right? I don't really want to have to pick and choose, okay? So what we would want to really ideally do is, and we can't quite do this, but you can think about it this way. I really want to include fixed effects for every state and every year, right? So what this is called would be two-way fixed effects, right? When I set this panel data up, no matter if I set it up by state and year or year by state, I really have two levels, right, that I would want to control for. So how could I do that, right? Well, if I set this data set up by year and state like we just were, and I wanted to include year fixed effects, that was just simply what we did up here. If I also want to include state fixed effects, what I could do is the exact same thing, but now I know this will include year fixed effects. What's another way we talked about I could include state fixed effects? Just using that IDOC command. It's going to create a dummy variable for every state, throw those into my regression. So this is essentially two-way fixed effects. I'm now controlling for things that don't vary within state across time and things that don't vary within the same time period across states. I'm eliminating even more omitted variable bias here, right? Now, the problem is I'm now going to have a dummy variable for every state and for every time period. What's going to happen to my R squared? My R squared is definitely going to go up. What's going to happen to my adjusted R squared? We don't know. It's going to be penalized because I'm now including even more variables, but I know that I'm going to have less variation that I can't explain in that Y variable now. So they're kind of working in opposite directions. Excuse me. So if I now run this regression, I include both levels of fixed effects. It shows me the state, but it absorbs those year fixed effects, right? But I'm including both. Now look at my coefficient. Oh, this is significantly different from when I only included year fixed effects. In fact, here I go from thinking that there's a pretty large impact of the mother's age on birth weight to something much smaller. And in fact, here, once I've controlled for year and time fixed effects, or year and time, year and state fixed effects, what essentially is the effect of the mother's age on birth weight? It's not 3.75 because it tells me that this effect is actually no different from zero. I can't reject the null. Right? That p-value is 0.6. I can't say that the impact of the mother's age actually is anything different from zero, or I now have gone to, in this two-way fixed effects model, finding that there is no effect. So this kind of shows, like, if I go to the next level where I include both things that control for factors that are time invariant within a state and then state invariant within the same time period, I've controlled for a lot of other things that I didn't have data on. I've eliminated a lot of different omitted variable bias. I now might find a coefficient that's not statistically different from zero. Okay. And this would be kind of the way, at least for the sake of this class, or it is, that we would kind of include those two-way fixed effects. Okay. Any questions? Okay. So, we'll open up this other data set, do a little bit of review, and then talk about the last thing that I wanted to make sure that we were hopefully we're going to get to today. So I have that other data set that's up on Canvas called GDP class data. I'm going to open that up and think about a very naive regression. So let's think about here. I have I believe this is, let's make sure what I have here. This is kind of weird. This is, why did I call this GDP class data? This isn't GDP at all. I mean, it's thinking about like the average income in what? Every county and every state. Okay. And it looks like I've got a bunch of different time periods. I have the unemployment rate in that county, state, year, and I have the average income. Okay. So if I run a very naive regression where I'm trying to predict the unemployment rate based off the average income in that county. So this might be the idea like, oh, where are most job losses coming from? Typically from lower paying jobs. So if I think about areas that have higher average incomes, I would expect to see on average like lower potential unemployment values, right? There's not as many kind of people unemployed, pulling the income level down. So I can kind of look at that very naive regression. Oh, if I run it. And I see, okay, when average income goes up by $1, I think it was measured in here. This must not be that. Was this in dollars or was it scaled? No, it must be in, I'm guessing if this is 66, this must be like 66,000, right? Or something like that. So here, if it goes up by what? 1 unit would be $1,000 essentially. The unemployment rate goes down by 0.07. And I think that was in terms of percentages. That's a pretty small effect. But it is statistically different from zero. So that's my very naive regression. But I then say, okay, well, look, I mean, there's a lot of things that impact unemployment that I'm not controlling for here that would also impact income, right? So the overall education level within that county and state, right, would impact both of those. I'm not controlling for that. So what I'm going to do is I have kind of two different subjects here. I'm going to try to set this up by state, county, and year. So if I try to do this, state, it gets mad. Right? So when I set up a data set to use this xtreg command, I have to do it using only one subject. Well, the issue here is my subjects are really like every combination of a different county and state, that's a different subject. So what I can do is I need to somehow capture that. But all I have in the data is the state and the county, right? I have to create a new variable that creates a unique number for every state county combination in order to use that XT set. So what I'll do is we can use some of the things we've talked about before, but something I don't think that we've actually used in this class. So I'm going to use this by sort command. I'm going to sort the data by state and county. So within each state and county, I'm going to have like 5 different years of observations here. What I'm going to do is create this new variable I call unique. And when I put equals underscore n equals 1, what it's going to do is put a 1 for the very first observation of that state and county, but only for that first observation. So if I do this for, I don't know, Atagua, I don't know how the hell to say that, but whatever this county is in Alabama, only the first time period gets a 1. Every other time period for that state and county gets a 0. But then when I move to the next county, Baldwin, Alabama, it only gets a 1 for this variable if it's the first year, 0 for every other year. Okay? So what I'm then going to do is say, okay, by this variable I've created, this unique variable, resort the data based off of this. So essentially what it does is it only kind of groups together those first years. It then says, within that kind of first year, create this state county ID only if, right, that unique variable is equal to 1, and then kind of underscore n just tells it to kind of fill it in. So if I do this, it now sorts the data. Well, all the zeros here doesn't do anything for. Okay. Let's see if we can get all the way down here. There we go. So what it does, oops, no. Hold on. Clicking to, I want to be able to show you the first one so I can kind of make this point. So it's now sorted the data by this year. So for every county, state, the first, Solano, California is now identified with a 1. Calhoun, Texas is now identified with a 2. McGreary, Kentucky is now identified by a 3. So what I now have is a new variable that for every state county, they have a unique number. So after that, well, this only did that for 2011. I want to make sure that or whatever it is, Solana, California has the value of 1 for every time period. So what I'm then going to do is say, by state and county, create this new variable, state county, that I want to use in my regression, like to set up my panel data, where it's the maximum of that state county ID I just created. What I now have is, For Kimball, Texas, it always has a value of 2,086. For King, Texas, that county state always has a value of 798. So I've now created a variable that I kind of had two subject levels, state and county. Well, this new variable I've created essentially creates state county unique numbers or unique IDs. So now when I want to include fixed effects, and I don't just want to do it by state or by county, I want each state and county to have its own dummy variable. That's a little bit different than creating a dummy variable for every state and a dummy variable for every county. Right? It's saying for every combination of this state county, create kind of a new dummy variable. So now when I set this panel data set up, I couldn't use multiple variables here for my subject, but I've now created a variable that captures that my subjects are state county combinations. So now when I set this data set up by state county ID and year, now it can actually do that. Okay. And now when I want to use this xtreg command, I'm running that same regression here. I guess I should have done this step by step. Sorry. I jumped the gun when I was coding this. Okay. So we'll call this. Here I was using state county fixed effects. So I'm using that same regression I was before, predicting unemployment rates by income. But now, what is it going to include fixed effects for? So what did I say when we use this FE command? It always includes fixed effects for whatever I put first. Okay? So how did I set this panel data up? By state county identifier year. So what will it include fixed effects for? Each unique state and county. So if I do that, I've now controlled for things within a state and county that don't vary across time. So I get kind of this coefficient, which is negative 0.24. I mean, that is significantly different than what I found from my naive regression, right? So instead of negative 0.07, right, that what? Grew by over 3 times. And that's because I've eliminated anything that would be consistent within that state and county across time. You can imagine, like every county is going to have like things that vary wildly, right, across those counties, but are consistent within those counties across time. Even something like weather, right? So, you know, same county is going to have similar weather patterns year to year. I don't have data on that, right? But I can control for that by using state county fixed effects. Now, I can also do two-way fixed effects again. So maybe I think there's things that don't vary across time within a state county, right? But there's also going to be things that don't vary within the same time period across these different counties. This is kind of the idea of COVID, right? It impacted, there were certain things that the restrictions in 2020 or 2019, however you want to classify it, impacted all counties equally. Right? So I can still do that two-way fixed effects where I'm essentially controlling for kind of state, county, and year by using that same fixed effects regression, but also including dummy variables for every single time period. If I then do this, I'm eliminating even more omitted variable bias. Kind of interesting thing here is I see a wild change in my coefficient. I also saw the sign change. So this is where, the more omitted variable bias we eliminate, we're getting closer and closer to the true causal effect. Without including these additional levels of control, right, these additional fixed effects, we are pretty far from a causal relationship. We still have a lot of omitted variable bias in our estimates. We're eliminating all of that omitted variable bias, shouldn't say all of it. We're eliminating a large majority of it, at least from things that don't vary within state across time and that don't vary within the same time period across states. That's going to be a lot of things, right? And we don't even need the data on it. That's like the power of these fixed effects regressions. I don't have to go out there and try to scramble to find these variables to throw in as additional controls. This fixed effects will kind of control for all those factors, even without having the data on them. Any questions here before we move in? Want more questions than not? All right. Hopefully this is kind of making sense. The last thing we'll do today is talk about, autocorrelation. So one thing that is going to cause an issue when we run these fixed effects models is when I create a dummy variable, let's say I wanted state level fixed effects, so things that are constant within a state across time. My errors from the previous time period are likely going to be correlated with the errors from the next time period. So even if I've controlled for these things that don't vary across time within a state, whatever I can't explain in the year 2010, it's likely I can't explain similar things in 2011. So my error terms are going to be correlated across these time periods. So the expected value of our error term, conditional on X, well, now what is one of our X variables? Well, it would be one of those state fixed effects or those year fixed effects. So now it's likely, because I've included those fixed effects, my errors across time periods might now be correlated, right? Because I've included in X are all my control variables, including these fixed effects. So that assumption is likely going to be kind of violated here. Whoops. So what we're going to do is there's a way to test for this to see, is there actually a correlation between my errors from time period T and time period T minus 1. Right? So T and T, that's like, are the errors in 2011 correlated with the errors in 2010? So what we're going to do is first assume that there is no autocorrelation. So if there is no autocorrelation, essentially, we can think about it as the correlation of these errors would be equal to 0. Okay. So if we do have correlation with our error terms, right, then we should see that this is not equal to -1/2, right? So where this comes from, we won't dive into kind of the mathematical proof, but it gets a little bit tricky here because assuming there is no autocorrelation, we essentially are saying that the correlation is equal to -0.5. So exactly where that comes from, maybe I'll go dive into an econometric textbook and pull up the mathematical proof and bring it into class Tuesday, but we're never going to have to show this. It's just that if that correlation between the error terms is -1/2, that means that we have no autocorrelation. So instead of testing against 0, we're now actually going to be testing against the value of -0.5. Assuming that we have no autocorrelation, if we had no autocorrelation, that correlation of the error terms would be -0.5. So we're then going to see, does our correlation vary from that value? So what we're going to do, and some things we've already talked about, just in a different way. So I'm going to first run my first difference regression. So that first difference regression we talked about on Tuesday, we're going to do that, right? Not use our fixed effects model. Now this would still produce the same coefficient estimate, it's just a little bit different. So we run this first difference regression. We then save our residuals, right? So if we went back a ways, we kind of said, we can save our predictions. We can also save kind of what our predictions are missing, or the actual Y minus the predicted Y. So once I save those residuals, those are essentially my errors for every single observation. Oops. I will then take my residuals from this current time period and run a regression where I'm trying to explain those with the current time period's errors or residuals. If that correlation coefficient is equal to if that coefficient estimate is equal to -0.5, that's telling me I have no autocorrelation. If I can reject the null there, that it's anything different from -0.5, I would say that I do have autocorrelation, and that's going to impact the reliability of my estimates. Okay, so we'll see kind of how we do this in Stata here. I think maybe this will help make a little bit more sense. So I'm going to keep using this same example, but we're now going to look at setting this up by state, county, and year, just like we did before. I'm now going to create, so once I have this set up as a panel data set, excuse me, and I think I showed this to you last class. We go back up here. Where is it at? We had our first difference regression. Oh, I didn't show you, sorry. Here I had the data set up so that it was easy. I would take 2007 minus 2006. If I had the data that looks like this, right? Well, it's sorted. So, if I look at this, I could think about, where's my year variable? There it is. I could take the income value from 2017, subtract 2016, but how do I do that? Well, if I've set this up as a panel data set, I can use this LDOT command, and it should work as if whether or not you put upper or lowercase l, right? What this will do is it says, okay, when I set this data set up as state, county by year, create this new variable called the unemployment rate difference. So what did we want with the first difference regression? We wanted the current year minus the old year. So using this LDOT command says take the current unemployment rate, subtract the unemployment rate from 1 period lag. That's why it's L. 1 period lag just means go back to the previous time period. So I'm going to do that for both the unemployment rate and the income variable. And what I'll see here is, really what did it do? It took the unemployment rate from the current year, minus the unemployment rate from the previous year. Oh, this went down by negative 0.9, right? So it's going to do that for now. What happens if we use the first difference or if we are doing first differences? Once I get back to the very first time period, so once I get back to the year 2011, do I have a value for Lake County, California from 2010? No. So when I create that first difference variable, I lose that year of data, right? I have no year before that. So we still kind of have a similar issue when I'm looking at kind of this autocorrelation. So I've got these difference variables. What I'm then going to do is run a regression of that unemployment rate difference on income difference, right? So it was the same regression I was using before, but now I'm using that first difference approach. So once I do that, I get this coefficient estimate, okay? What I'm then going to do is use my predict command. Now, usually in the past, when we use this predict command, it was trying to predict the Y values. So if we take the actual Y minus the predicted, that would give us our error term or our residual, right? So I'm going to save this. And if if you wanted to, you don't have to call this residuals. If it helps you, think about this easier, you could call this errors, right? You're just kind of predicting your errors, but you have to kind of tell Stata only recognizes errors as the word residuals, right? So predict residuals will give me those errors. So I'm going to do that, save those residuals from my first difference regression. It's going to save them as a new variable, okay? So once I do that, that was kind of my next step. Oh, and now I scrolled too far. Where am I? There we are. I'm then going to run a regression where I take the current errors or the current residuals and I try to predict them using the prior year's errors or the prior year's residuals. Now, once again, you can use uppercase or lowercase l here. Okay. Now, when we're looking at this autocorrelation, we're not looking for the coefficient estimate. We're just looking for that correlation between those two. So what we're actually going to do is we don't want to include a constant here. Okay? So I just want to pick up for, is there a correlation between my errors? I could run this regression, but not include a constant. Now, here's where we're going to have to use something called clustering standard errors, right? So this kind of resolves an issue that I think there might be some. So here, if I'm looking at the correlation of my residuals, this is going to be something that I might think there are things that would impact every time period within a state and county similar. And so that kind of controls for any value that would be in those errors that's consistent, but not predictive of the following years. So this is a little bit into the weeds for this class, but this is what we would have to include in order to correctly run this autocorrelation, or I think it's called the Wooldridge something test. I forget the other economist names that are associated with it. So we run this regression. We then look at that coefficient. Well, it looks like it's different from negative 0.5, right? But when I look at the regression output, the p-value here tells me whether or not it's different from 0. That's not what we actually want for this autocorrelation test. We want to know, is it statistically different from negative 0.5? Now, this goes all the way back to like when we were talking about means. Right? So usually, when we're calculating test statistics, for coefficient estimates, this is kind of what we've gotten down to, right? But really what we're doing, we just kind of leave it out, or I leave it out because I'm lazy. The assumed true value of every coefficient is actually 0. Well, that doesn't do anything. Well, here, we're not testing for whether or not that coefficient is different from 0. We're testing for, is that coefficient different from negative 0.5, right? Which actually in this case, we would actually be saying, is it different from, how much does it vary from 0.5? Well, that's going to be very different from how much it varies from 0. So I'm going to get a very different test statistic if I test against 0 compared to if I test against negative 0.5, right? But when I look at the regression output, it always defaults to testing against that value of 0, which is not what I wanted for this autocorrelation test. So what I then need to do is say, okay, using that coefficient estimate, I actually want to test to see, is the coefficient on that lagged residuals, not is it different from 0, but is it different from negative 0.5? So that's all this is doing here. It's saying, don't run a hypothesis test like you did here against 0, run it against negative 0.5. It then reports to me that p-value, which here doesn't really change anything because it's still 0. So it would still kind of be the same statistical significance. But in different examples, it could change that p-value I see. So if I just looked at this regression result of my current errors on the prior errors, it could lead me to either reject or fail to reject, when if I test it against not the value of 0, but negative 0.5, maybe I fail to reject there, or kind of vice versa what my other decision was. Okay. Any questions on kind of this step that we would use? So kind of here, this was like step 1 was to run that first difference regression. Step 2, kind of save these predicted residuals. Step 3, run our regression without a constant of the current residuals on the previous residuals. And then step 4, I test the coefficient on that lagged residual term against negative 0.5. So this is what I was saying here. These were our 4 steps. So I'll redo that do file and kind of replace it. So I include some of these comments that I just threw in, and I'll make it a little bit prettier and kind of easy to read. But essentially, those are the 4 steps that we have outlined in this slide. If I do find that this is different from negative 0.5, remember, what we were starting out assuming is if it's equal to negative 0.5, I have no autocorrelation. I don't have to worry. If it's statistically different from negative 0.5, which here with a p-value of 0, it definitely is, I do have autocorrelation. So that's bad. But the good news is, for us, we have stata, or R. There are very easy ways to adjust for this autocorrelation. So autocorrelation doesn't cause us issues with the coefficient estimate. It causes issues with our statistical significance. So if I come down here, if instead, so I did something like use XT-reg, and I'm going to here include like year fixed effects. Well, if I have autocorrelation, right, I want to control for that. What I can do is kind of use this VCE command and cluster at whatever level. So here, before we were looking at the state county level, I cluster my errors by that subject. And what I end up with is the same coefficient, but when I cluster those standard errors, my standard error goes from 0.0019 to 0.0029. So it adjusts my standard errors for this autocorrelation. Okay? So that could change things. In this case, I don't think it does, right? In both situations, this is statistically insignificant. However, this is less statistically insignificant than this. I mean, a p-value going from 0.3 to 0.5 is a pretty big change. And you can imagine maybe it goes from 0.03 to 0.1, in which case that would change our rejection decision. So we can test for autocorrelation using this four-step process. If we in fact reject that null that it's equal to negative 0.5, that means we do have autocorrelation and need to adjust for it. The good news is the simple adjustment is I can use this VCE command along with that kind of xtreg syntax with these kind of built-in programs behind the scenes. Okay. So I think next class, I've got a different data set with some traffic fatality data. We actually might kind of revisit some of these topics. We're then going to jump into the final topic we have, which I've already got up here. I just don't have it on the main homepage yet, which is what we call instrumental variables. So if I recall correctly, if I can get this to pull up here, I'll get you out of here in the next minute or two. Okay, well, it's being slow, but we don't, yeah, I can see it's going to take a few minutes. So we don't have like a ton of slides to go through. Once again, we won't dive as much into the theoretical side of instrumental variables, more of how we do this in Stata and kind of read Stata's output. So I probably will take a little bit of time Tuesday to just go through that other example, revisit some of this panel data stuff, and then we'll kind of jump into instrumental variables, and that'll be the last topic that we have. So I'll get that final problem set posted up sometime tomorrow. You've got those practice problems. You can start reviewing those. Now, we haven't talked about instrumental variables, so like the first half will really be the only thing that makes sense. But you can kind of see here, I've got what, 9 slides here. So we're going to spend a lot of more time in kind of Stata next week than we are kind of the theoretical side of things. I will have regularly scheduled office hours next week. I'm going to start working on that problem set after tomorrow when it gets posted. If you have any other questions, feel free to kind of stop by. Otherwise, enjoy the weather, fun, safe weekend, and I'll see you guys on Tuesday.